Now let's talk a little bit about how energy can be transferred in thermal systems. Last time we said that temperature is proportional to internal energy. We can be explicit about this. We know that the internal energy is equal to the number of particles times the average kinetic energy. And the average kinetic energy was just 3/2 kBt, which means that the total internal energy is just 3/2 times the number of particles times Boltzmann constant times the temperature. So we can actually know the internal energy at any state as long as we know the temperature and number of particles of that system. In the last example, we saw that T was constant. In that case, the internal energy was also constant throughout the whole process. Just like we did in energy conservation, we know that the system can gain or lose energy. And just like we saw in energy conservation, the system can change energy through gaining or losing heat or heat transfer and doing or having work done on it. And so these are two ways that our thermal systems can also lose or gain energy. In the last example, both work and heat transfer occurred, but they exactly canceled to make it so that the total internal energy of the system was constant. We'll talk about this more later when we talk about specific thermodynamic processes. Let's talk a little bit more about heat transfer. Heat transfer occurs through heat flow, or the transfer of energy due to a change in temperature. Heat is the energy that is transferred by heat flow. We use Q or delta Q, and the units of heat are joules. A heat capacity is a constant in proportionality between heat and temperature. This depends on the material that you're using, and we use the abbreviation C for heat capacity. The units of heat capacity are typically joules per Kelvin. And we can write an equation such as this. So the change in heat, or the heat that is transferred, is equal to the heat capacity C times the change in temperature. Calorimetry is a word that stands for an experimental technique, which is the measurement of the heat capacity of a particular material. So again, starting with heat capacity, this is just assuming that that's a total material property, but doesn't take into account how much material is there. We know often that it takes longer, let's say, to heat up a big pot of boiling water than it does to heat up a little tiny bit of boiling water. And so sometimes it makes sense to actually include the amount of matter that you're talking about heating. One way we do that is through the specific heat. This is the heat capacity per gram of material, and the units are joules per gram Kelvin. And you can see that the heat equation is the same, except for instead of capital C, we have a little c, which is the heat capacity times the mass, and this is the mass in grams, which I understand is not an SI unit. We can also have the molar heat capacity. This is the heat capacity, obviously, per unit mole of the material, and the units are joules per mole Kelvin, and in this case we can use C prime and multiply that by N, and that gives us the constant in proportionality between the heat transfer and the change in temperature. We can also add heat to systems and cause phase transitions. So if we start with some ice and it starts as a solid, but it's in a room that is warm, we see that we can get the ice to start to melt, and at which point we have a solid and liquid phase coexistence. And then finally, the ice will completely melt and become a liquid. And when we do this, there's this phase transition. Heat is being added and being absorbed by the system, but there is no change in temperature. So if we try to use the traditional change in Q is proportional to change in T, we'd actually find that the change in T was 0 during this process. And yet we know heat must have been absorbed by the ice cube in order to cause it to melt. So what's being done? In this case, heat is being used not to change the temperature of something, but rather to break the chemical bonds. And we can write a new equation, which is delta Q is equal to L times M, where L is the latent heat, which is also a constant of proportionality, and M is the mass of the system. So the latent heat, again, is the energy transfer per unit mass required to break or build the bonds between molecules. You can have latent heat of evaporation, latent heat or a latent heat of condensation, and that's just going in different directions, whether you're causing a liquid to evaporate into a gas phase, or if you have a gas that is condensing into a liquid phase, for instance. Again, we use the units of L, and the unit is units of joules per gram in this case. Another way that we can transfer energy is through work, which is what we talked about a lot when we were talking about dynamics for exam 2. And we talked about it also when we were talking about the first part of conservation of energy for the upcoming exam, which will happen next week. So remember back to our general expression for work. We say that work is equal to force times distance times the cosine of theta between those two vectors, the force vector and the displacement vector. And for instance, you can have a block which has a force applied to it at a 45-degree angle. This angle is theta. And you can see it might only displace in the horizontal direction, and that will be the displacement d. And so as the force is applied, you can see that there's a displacement. So we have this equation, work is equal to force times displacement cosine theta, but we need to know what the force is, what the displacement is, and what the angle is. And we'll do this again using our model piston system that we have shown over to the side. It seems like it might be quite difficult to figure out what this force is or what this displacement is, but it actually is quite simple because we know that the pressure is proportional to the force per unit area. And again, I'm showing you now this piston and looking down on it from the top, where you can see that the area that we're talking about is the cross-sectional area of the piston, A. Yes, it's true that there are forces acting on the other ones, but this part of the piston is the only part that can move due to a force, and so it's the only part that work can be done on the piston is on the lid. We also have this displacement. In this case, this is the displacement in the y direction due to the force that's being applied to the lid. And so in this case, the force up or down is in the same direction as the displacement of the lid, up or down, and that implies that the angle that we're talking about here is 0. That simplifies our work equation so that work is just equal to force times displacement. Again, we can replace this force by saying it's equal to pressure times the area, where the area is the area of the lid, and the displacement is just equal to the change in the y location, the displacement of the lid in the y direction. Putting this in a kind of slightly different way, we can bring the pressure outside and say it's equal to the pressure times the area times dy. For this piston, we have a fixed area. When the piston lowers by amount dy, the amount of volume that is changed is just proportional to the area times the change in y. So that says that the area times the change in y is just equal to the change in the volume of the gas in the piston. This makes our life a lot simpler. This means that we can reduce our work equation from FD to be equal to the pressure times change in the volume. So work of this system is just the pressure times the change in volume. If we want to look at our PV diagram and we have a piston that's moved, let's say it starts at an initial pressure and volume, which is given by this purple dot. If we assume that the volume changes but the pressure stays constant, then we have a second state which has a different volume but the same pressure. If that's the case, then the amount of volume that has changed is just given by the difference between V1 and V2. And we can see from this equation that the work done by this transformation from the first volume to the second volume at the same pressure is just given by the area inside this shaded box. So the work is equal to the pressure times the change in volume. This is general, so if instead we have a system where P1 and V1 are related to each other but have the same temperature like we did in our example earlier, we know that the delta V might even be the same as the last example, but because now P is now a function of the volume, we can actually see that the work done in this system is going to be greater because the pressure is actually different as you go from P1 to V1 along this path. So even though the delta V is going to be the same here, you're actually going to have more work done by the system in this case when you have the temperature constant instead of the pressure constant. We'll talk more about this in a few slides. So putting all of this together, we can see that you have a variety of energy transfers that can change the amount of energy you have in your system. In particular, you can have a change in the heat. You can have a heat transfer or you can do work. And either one of these can either add energy to the system or take it away. How do we know which one will do which? If we add heat to a system, so the change in Q is greater than 0, then we must be adding energy to the system. If heat is taken away from the system, then the change in Q is less than 0, and we will be losing energy from the system. If the work done by the system, delta W, is greater than 0, then the system will lose energy because work is being done by the system. If the work is done on the system, then the system will gain energy. Let's explain that a little bit slower. If instead we write it like this, where the delta Q is increasing, heat is being added to the system, then we know that U is also increasing. On the other hand, if the amount of work that the system does is increasing, that implies that the energy of the system must be decreasing because it's losing energy due to work. In this sense, we've defined work in such a way that it's similar to friction, which also took away from the internal energy or from the total energy of a system. All of this put together gives us the first law of thermodynamics, which is an energy conservation law. It says that the change in total internal energy of the system is equal to the change in the heat transferred to the system minus the work done by the system.